I know they said that's what the plan was. That's kind of what they do, pretty much so. Yeah, okay, so 21, let's see what happens with that. You say the one on the bottom is bigger than on the top. So Norway, that's it, right? 2002, 4.7 times 10 to the 7th kilograms of ground coffee was consumed. Norwegians drink a lot of coffee, did you know that? At least stereotypically they do. What did you say?
What's the number one?
Number one in
Per person.
per person in coffee consumption? Okay, so if it's like this, kilograms of coffee, and the population is 4,525 people. We want to know what it is per one? No, to brew a typical cup of coffee, you need 10.6 grams of coffee. Determine the coffee consumption in terms of cups per person. Ooh. Well, if we did kilograms per person, then could we go, this is like a rate conversion, 10.6 grams of coffee per cup. So let's do this. Let's just write that down, 10.6 grams per 1 cup. We could also write 1 cup per 10.6 grams. That would be pretty good. To brew coffee consumption in cups per person. So if we get kilograms per person, then we can use the grams per cup. And then we can come up with cups. So what do you do here? Can you change that into kilograms per 1 person? I mean, what's 4.7 times 10 to the 7th power equal to? How many place values do we move the decimal point? 7 places. So 1 place, 2, 3, 4, 5, 6, 7. And then we have 4, 5, 2, 5, 0, 0, 0. So what I would do is I would cross out the 3 zeros top and bottom, and then I'd just do that division. So you have the calculators. What's 47,000 divided by 4,525? It's like 10 point something. What is it? What do you get?
It's 11.05.
Oh, 11.05. Is there any more? Or is that it? 0.05?
No, there's more.
Let's go. What is the rest of it?
3, 6, 2, 1, 8, 3.
And then we're out of place values, right? That's an ugly number. So you know what I would do? I would leave it like this.
Trent typed it in wrong.
Oh. Okay, Trenton, what should it be, somebody? What do you have, Fiona? For this division, what do you have?
I know, gosh. If it was 4, 5, 2, 5, not 4, 2, 5.
Is that 4033? Yeah. Okay, that's still an ugly number, right? So here's what I would do. I would leave this like this. And this is the number of persons. And this is the number of kilograms. I would leave that fraction there. So I think because this is in grams, this should be changed to grams. 47,000 kilograms is how many grams? What's bigger, a kilogram or a gram? How many times bigger? thousand, so how many grams will that be? 47 or 47 million. Do it like this, 1,000 grams per 1 kilogram. Do a unit rate conversion or a unit conversion like I've taught you. The kilograms cancel. Now it's 47 million grams per 4,525 people. And now we're going to multiply by one of these two to change it to get cups up on the top. Because then we'll have cups per people. So which of those, the top one or the bottom one, do you multiply by? So we're changing grams into cups. What did you say? The bottom one. 1 cup for every 10.6 grams. Yes, because then grams will cancel. And now you have this times 1 divided by this times this. So here's how you got to enter this into your calculator. 47 million divided by 4525 times 10.6 equals, what do you got? You have to put those parentheses in there though, or else it's going to come out goofy, I think. Yeah, it will.
I got an answer.
What do you have for an answer?
2.254355.
Okay, that's good enough. Cups per person? So really?
I got 979.881166.
You have 979 cups a person?
That's what I got.
This is a year, right? Yeah, so I don't know what you did there. I think you probably divided by this number, then multiplied by 10.6.
I think I did something wrong, but yeah.
So you got your 47 million divided by parentheses. 4525 times 10.6 parentheses equals. Yeah, I got what you got. 979.8. So let's just round it up. 980 cups a person a year. How many cups a day? Divided by? How many days in a year? 360. So that's only 2.7 cups a person a day. But that's every man, woman, child, infant, person on life support, everybody. So if you figure what? 2/3 of the people drink coffee, then it'd be, if 2/3 of the people drink coffee because of all the young kids and what have you, that's 4 cups a day. How many cups of coffee you drink a day? 0. How many you drink? You drink coffee? You should. You drink coffee? You drink coffee? You guys don't drink coffee? None of you do? Yeah. I drink coffee. It's the first thing I do in the morning. Drank coffee before I went out on the snowblower this morning. My wife won't even get out of the bed if there isn't coffee being made. All right. Any other problems, or shall we move forward?
I had question 21, but I think I understand one. How?
World population was approximately 6.446 times. Oh yeah. 6.446 times 10 to the 9th. That's billion. So that's 6.446 billion people. Global oil output was 8.0 times 10 to the 7th times 10 to the 7th million. So that's like, when you write that, you got to write a million in as like a power of 10 again. And then a barrel is 350 gallons of oil. I'm going to write that. 1 barrel is 3.5 gallons. how many barrels of oil is this per person per day? So this is the number of persons. This is the amount of oil. So then we have to go times 10 to what power for a million? What is a million in terms of 10 to the power of? 6. 9 is billion. That's billion, and 6's are millions, and 3 is thousands. Okay. So if we did this work right here, we would have persons per barrels. Is that what we want? No, barrels per person, so we gotta flip it. We gotta take a reciprocal rate. So I'm not gonna put 0.0. Times 7 times that. So this is barrels per 6.446 times 10 to the 9th persons. And then we can use this here to figure out how many gallons of oil a person uses a day. So if we're gonna multiply that by this fraction, will that give you gallons on the top? You see, we need to have gallons per person. If I put 1 barrel up here and 35 gallons down here, does that work? And look. Are the units going to cancel?
Yeah.
Well, you're going to have barrels times barrels.
No.
That doesn't work. You got to flip this. Maybe 35 gallons for 1 barrel. Now when you write this out, your barrels will be multiplied by 35, so you have more gallons. That's what you'd expect. These are gone. But to enter all that into the calculator is a mess. So what they want us to do here is they want us to use this idea of the quotient of powers to get rid of some of these numbers. Let's do this. Together, that's 10 to what power? 13th. And then there's 9 down here. So you could think of this as 10 to the 13th minus 9. So that's 10 to the 4th. There you go. Now that is a lot easier to do in a calculator, because 10 to the 4th is just 4 place values. So in the calculator, this number is 80,000 on the top, times 35, divided by 6.446. And that gives us our gallons per 1 person. So what is that? Multiply it up and divide. I gotta do it too, just to see what I get. What do you get? $434,377 and change. Actually, it goes 378 if we round it. Gallons per person, and that's per year, right? Because this is the oil per year. So how do I change that into per day? Yeah, we're going to divide by 365 days in 1 year. See, this is per person per year. So the years go away. So take that number, just keep typing, divided by 365. So on average, you use 1,190 gallons of oil a day. Crude oil. Now, You guys know a little bit about the world, right? Do you think you use more or less than that? You're an American. Who uses the most oil per person? Americans. You live in Alaska. Who uses the most oil per day of the US population? Alaskans. Not because we have oil. What's that? We need heat. We need a lot of light. We travel. You may look at that ferry comes in and it hauls 100 people out of here. Sucks a lot of oil. And then people that leave the state, how do we get out of the state? We fly. That costs a lot of energy. Alaskans are very, very high on the energy consumption per person. And we just don't have very many people here. I don't know what it is. I don't know what the number is, but it's way in the heck above that. Way, way, way above this. You think about it, even if it's 1,000 gallons a day, that's for everything we do. You gotta remember clothing, food transportation, on and on and on. And then, yeah, how do we get our food up here? We barge it and fly it. A lot of the produce gets flown to Juneau. Alaska Air's got those 737s that they just fill up with those big, huge containers that are shaped like the fuselage of the jet. That's how they get food up to Fairbanks, produce and stuff. It's spendy. Down in the States, it's all trucks and trains. Trains are cheap. Yeah, lifestyle is like that. It's different. Americans are different. Americans all drive cars. Go to Europe, they don't drive cars. Can't afford to. They go on public transportation. They have trains, but everybody's close and compact, so it's a lot easier. So, any more questions, or should we go on and do something else? You guys, do something else? 8-4, negative exponents. Okay, so we have a couple. We've got this one. We've got this one. We've got this one. Is that it? Is it 3 right now? We have 3 properties of exponents that we're working with. I feel like there was a 4th one, but maybe not. Power of a power, power of a product, and quotient of powers. Okay, so here's the next one. And this one, oh, let's see. How do we, the best way to show it to you? I've shown it to you before. I've shown it to you with a number line. And I still like the number line because you can reconstruct a number line. And this works for any value other than 0. And if we, I won't make a big number line, but let's say we did this. Let's say we multiplied everything by 2 as we move across the number line. So 2 times 2 is 4. 4 times 2 is? Times 2 is?
16.
Times 2 is? Okay, it's 32. So let's write those as powers of base 2. Because when we multiply by 2, that's the same as an exponent base 2. So 4 is going to be 2 to the what power? 2. And then 8 is 2 to the, and the 4th, and to the 5th. So let's go back. So 2 then must be 2 to what power? just gotta be the first power, yes. And then, we've done this before, but we'll do it again. If you move to the right, we just multiplied by 2, didn't we? I said times 2, times 2, times 2. So that's times 2, that's times 2. How do you move to the left? Divide by 2. Good. And then divide by 2. And divide by 2. Oops. So now what's 2 divided by 2? What's 2 divided by 2? Which is 1. So that's 2 to the 0th power. So you get the 0 exponent property. E to the 0 is equal to 1. And these all work. And B is not equal to 0. Okay, so let's keep going. What's 1 divided by 2?
1/2.
It's 1/2. And that's how I want you to think of division. Think of it like this, 1 divided by 2. And as we move to the right, or to the left, when we went from 4 to 2, we could think of that as 4 divided by 2. So when we move to the left, this division by 2, and this is where we need to be going in algebra. We need to not be thinking of division by 2. We need to be thinking of multiplication by the reciprocal. Because that brings into play this whole idea that if you have A divided by B, that's the same as A multiplied by the reciprocal of B. So that just looks like this, A over B. What I'm writing up here is going to be a very nice short list of good notes. Okay, so we move to the left, we multiply by 1/2. So what's half of 1? You said is 1/2. So that's 2 to the negative first power. So 2 to the negative second power is going to be 1/2 times 1/2. What's 1/2 times 1/2? It's 1/4. And then 2 to the negative third power is going to be 1/8. And 2 to the negative, and this can, we can go for as long as we want. That's 1/16. And 2 to the negative fifth is 1/32. So why I do this is to show you the relationships here. For example, take 2 to the negative first and 2 to the positive first. 1/2 and 2. Maybe more importantly, 2 to the negative first is equal to 1/2. And 1/2 is the same as 1 over 2 to the first. So what I'm doing is I'm going to write that fraction with an exponent in the numerator, or in the denominator. Let's do another one. Say 2 to the negative third is 1 over 8. And that's the same as 1 over 2 to the third. So if we cut out the middleman here, 2 to the negative third is same as flipping it upside down and changing the power from the negative to the positive. Yeah. 2 to the negative fourth is equal to 1/16. 16 is 4. So this is 1 over 2 to the, because that's, I'm sorry, what am I doing? Because that's 16, 2 to the 4th is 16. So whenever we have a negative exponent, we can rewrite it as a positive exponent by taking the reciprocal of it. We can do the same thing on the bottom. If you had something like this, 1 over 2 to the negative 4th, that becomes 2 to the positive 4th. And if you really need to know, 1 divided by, well, that's 1/16, isn't it? 1 divided by 1/16 is the same as this. And then if we use the multiplication by the reciprocal, that's this. So that number is the same as this number. That's negative exponent property. Then it's a matter of using it. So let's write it over here. So b to the negative n is equal to 1 over b to the positive n. That's the negative exponent property. And it gets used a lot. It gets used in scientific notation, it gets used in chemistry, it gets used in physics a great deal. So the ways that they might ask us to use it, I mean, you could have something like this. Here's an example. It's like a to the 7th multiplied by a, I think, to the negative 4th. It doesn't matter. We'll use those numbers. So in this case here, if we use the property like this, you could rewrite this as a to the 7th times 1 over a to the 4th. This is where it starts getting all twisted and bent. Watch. So this becomes a to the 7 minus 4, right? Using the quotients. So that's a to the 3rd. Or you could just do this. You could use the products property, where you add the exponents. So that's a to the 7th plus a negative 4, which is the same as a to the 3rd. So there's more than one way to get there. And if you get into higher level math, or when you get in there, there's ways that we write proofs, line by line by line, using all the different properties to prove that this really comes from this. And I kind of showed you that by showing this other pathway. So, then there's another property that's related to this one. It's called the negative exponent property for fractions. And that works like this. So you could have, for example, a fraction that's written like this. And it could be to the 4th power, for example. And that would just simply mean that you take a to the 4th power, and you would take b to the 4th power, because that's how you multiply out fractions. That's the same. This comes from the quotients idea, right? Except we have different bases now, so we can't use that property to simplify it. Now, let's say we had something like this. We had a over b, but it was to the negative 2nd power. So now what you would have is you would have a to the negative 2nd over b to the negative 2nd. So what you do is you treat each of these as individual terms. So how could you write a to the negative 2nd as a positive power? Yeah, take the reciprocal and flip it. So then A goes down to the bottom, and a 1 goes on the top. So then here, since this is a denominator, the same thing. You write as a reciprocal and you flip it. So what you do is you have things go in their kind of like the opposite direction. And then they get, one goes to the top, the other goes to the bottom, and then they get the opposite sign. Go from a -2 to a +2. So in this case here, there's a 2 for both the B and the A, so we could rewrite that as B over A to the second. So this flips into this. So that's the negative exponent property as it applies to a fraction. We just do the whole thing. So now if I have, what do they use for variables in the book? They use x and y and n. So they use x over y to the negative nth power is equal to y over x to the positive nth power. So we got the 0 exponent, 1, 2, 3, 4, 5 of these right now, plus the 0 exponent, plus remember dividing fractions property. And then, of course, a lot of this just turns into crunching numbers. Looking at numbers, applying the properties to rewrite them the way they ask us to. So you give us something like this here, 1 over m squared taken to some power. Let's say we just do it this way, to the -3rd. So there's several ways to go about this. You could put that's to the -3rd, this one to the -3rd, and then use a property to change that to the -6th. Or you can just look at this, apply to the entire fraction, use the property, and flip it. So now you have m squared over 1, all to the positive 3rd power. We don't have to worry about 1 because 1 to the 3rd power is still 1. And then you come over here, use the power of a power. So the power of a power means that this is going to turn into 2 times 3, which is 6. And if it's over 1, just write it the way it is over. Just leave it like that. So this is equal to that. So we can take something that initially gets written kind of confusing and change it to something that looks much more familiar and easy to deal with. Ten years ago, Den put money into a college savings account at an annual yield of 6%. You thought we were done with that, huh? If the money is now worth $94.91.49, what was the amount initially invested? Yeah. When you walked in yesterday, actually, there was stuff on the board from Algebra II doing exactly this kind of problem. This is one to make note of, because we can go back in time with investments. Let me explain to you how that looks. Like, if you have this beginning amount of money and it goes up, 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 up over time, that's what it started at. But we can also think backwards in time. This is like time 0. This is in the past. This is the future. So this exponential line, this equation, goes through the negatives and the positives. So in this problem here, they say that the interest rate is 6%. The money that it's now worth, so remember the equation? A, P, what goes in parentheses? This is the amount you get, that's what your principal, 1 plus
Which is
R to the T. So this is T years, and this is the amount of money you get. And then they say you got 94 9149. That's what he has now, after 10 years. So what we have to do is we got to figure out what he started with. So here's what you can do. You can say that this is the starting amount, but when you go to t, you go back in time 10 years and you use a negative exponent. So we want to know, this is going to tell us what he started with. He's got 94, 91, 49 times 1 plus, how do I write 6%? 0.06. And then it's to the negative 10 because it's back in time 10 years. So you can do it on your calculator. But what they'd like you to do is use the property here, or like over here, maybe this version of it, to take a part of this and turn it into a positive exponent. So in this case here, you have 9491.49, but this whole thing can be written in the denominator position if we change the exponent to a positive 10. So this is 1.06 raised to the 10th power. So in your calculator, the way you can punch this thing out is 949.40. Is this the right number? 940, ooh, I'm missing a 1 in here. 9491.49 divided by 1.06 raised to the 10th and hit equals. And that'll tell you how much they started with. So it's following this same curve, but it's saying that now we're at $9,491.49. So if you go back along that curve, where did it have to start from? What's your answer? What do you get? I hear you clicking.
I'm good, but I'm waiting for somebody else's answer.
Oh, tell me what you got. I'll tell you whether it makes sense.
Alright, 5,299.41.
Point, how much?
998,441.
Like this? Like that? And it keeps going? So maybe $5,300? Yeah, 5,300. I bet if you put 5,300 in, and then you just did times 1.06 to the 10th power, I bet you it comes out. All right. Okay, then the last kind of thing, big uglies. They'll do stuff like this to us. And these are just exercises where we have 5a to the 4th, b to the 7th, c to the 2nd, 15a to the 11th, b to the 5th, and c to the 3rd. And they want us to write the whole thing without negative exponents. And there's so many ways to go about this, you guys. There's so many different ways. So if you see another way, that's fine. First of all, this has to be handled separately. So can you simplify 5 over 15? What does it become? Five over 15. 1 over 3. You have 1, I'm not even going to put a 1 up there. Well, I guess we'll put it up there. Because you never know if all of the variables disappear from the top. You need to have something up there. So 1 over 3. Okay, then if you did this one right here, there's more a's on the bottom, right? So if you just cancel them out, you'd have all these a's in the denominator position. So if you think of this portion here as a times a times a, and then you've got 1, 2, 3, 4, 5, 6, 7, 10, 1, 2, 3, 4, 5, 6, 7, 8. That's 11 of them. Those four cancel out, and you're left with 1, 2, 3, 4, 5, 6, 7. So this is just a to the 7th. Now, where are there more b's, top or bottom? And how many more are there? 2. Because 7 will have 5 canceled off and leave 2 behind. And then where are there more c's? So then you can have just c to the first power. That's it. Now, some people might have taken this one here, like a to the 4th minus 11, and get a to the negative 7. But then that would have been in the numerator position, and then you have to change the sign when you put it down below and make it a positive. It's real mechanical. Have fun. Let's see how these goes. What do I have for